In this video, we will talk about the concepts of momentum and collision. More so than other concepts in physics, the idea of momentum in popular culture and in everyday language typically differs from how it is used in physics. Regardless of how it is used beyond the scope of physics, momentum can be thought of as the quantity of motion of a moving body, measured as a product of its mass and velocity. So when I'm thinking about momentum in physics, I try to remember mass and velocity. Because velocity, a vector which consists of a magnitude and a direction, is multiplied by mass, a scalar, which only consists of a magnitude, the product results in a vector that is scaled. To sum that up, momentum is a vector which has magnitude and direction and is typically denoted by using a lowercase letter p. Closely related to momentum is the concept of collisions. In this course, two types of collisions are talked about: elastic collisions and inelastic collisions. The two types of collisions differ mainly regarding the conservation of kinetic energy. In an elastic collision, kinetic energy is conserved, meaning the kinetic energy before the collision is equal to the kinetic energy after the collision. Conversely, in elastic collisions, the kinetic energy is not conserved and energy is lost in some other form such as sound, light, or heat. It can also be lost in doing work on an object by deforming its shape. Let's take a look at an example that combines momentum and collisions. Two cars collide in a head-on collision. One car with a mass of 1,000 kilograms was traveling north at a speed of 40 miles per hour, and the other car with a mass of 1,500 kilograms was traveling south at a speed of 45 miles per hour. The cars stuck together, lost no mass, and continued to travel as one unit after they collided. What is the final speed of the car? Traveling in opposite directions. One velocity is positive and one velocity is negative. Using the concept of conserved momentum, the momentum before the collision and after the collision remains the same. So, the momentum initial equals the momentum final, which means that the mass of car 1 times the velocity of car 1 plus the mass of car 2 times the velocity of car 2 equals the whole unit's final mass times the final velocity of the whole unit. Because the cars travel in one piece afterwards, we can add the two initial masses to find the final mass. In regards to direction, the final unit will continue to travel in the same direction as the direction the car with the greater momentum was traveling.